Okay, welcome back everybody. We today are going to be talking about the next part of Chapter 1, Section 3, which is compounding interest rates. So compounding interest rates follow the same basic formula as exponential decay with two changes. So the formula is the amount is going to be equal to the principal times 1 plus, that's the first change, the rate divided by, I'm going to call this n, which is the number of times it's compounded, to the power of is the number of times it's compounded. So let's just kind of explain here. Now you might have been taught this formula slightly differently, but it's essentially the same form. So A is the amount, P is the principal or starting amount. This time I'm going to call it principal. R is the interest rate as a decimal. N is the number of times compounded per year. Generally, in the quote-unquote real world, this N is going to be 12 because it's very uncommon to find an interest rate that isn't compounded monthly. And then T is the number of compounding periods, which if it's monthly and it's over 5 years, you'd have to do 12 times 5. So we'll call this number of being all right. So let's start with something easy. Let's say that you buy a car, and car or truck or whatever. It costs, let's use a nice number, $10,000. Say that you get it at 5%, what's called APR, which is annual percentage rate. That's the rate that interest would accrue through the entire year, but because it gets compounded monthly, it ends up being higher than 5%. 5% APR with a term of 5 years. All right, now we want to find out how much is this going to cost. Total cost. Now you might want to just do 10,000 times 0.05 times 5 and think that that's going to be the amount of interest, and then add that on to 10,000, and that would work if interest were simple, but it's not. Instead, what banks will do is they'll take a month and they'll find out how much interest accrues on that month and then add that to the loan, so that the next month there's slightly more interest than there was the previous month, and that'll happen through the entire lifetime of the loan. And when you borrow money for a car, they do that calculation all at once, which is why it matters the number of years. So if you end up going for, say, a 6-year term, that amount of money is spread out further, so it seems like you're paying less because your monthly payment will be lower, but over the lifetime of the loan, you end up paying, in some cases, significantly more. All right, so how much total cost? So the amount, the total cost, is going to be equal to the principal, 1,000, times, in parentheses, 1 plus the rate is 5%, 0.05. And again, almost everything in real life compounds monthly. If you do certain kinds of bonds or deposit certificates, those will compound quarterly, depending. It depends on the bank. And then the number of times it's compounded. So this wouldn't be 5 because we're compounding monthly. It's going to be 60, which is 5 times 12. All right, again, I'm going to use my calculator to evaluate this. I might go forward, or I might just let you watch me fumble with my calculator. And then this is 2. So you end up paying over the life of the loan $12,833 And again, we're going to round to cents because that's what they would do. 50. Now, what if it were 6 years? You might expect this just to be 10,000 times 0.05 more, but it's not going to be that. So if I just do this exact same thing, but instead change this from 60 to 72. So I'm just going to go back and change my last equation. It ends up being 13,490 cents. So you're getting about almost $1,000, about $600 more that you would have to pay. Now, the reason that this happens is when you're actually doing your loan paperwork, they won't focus on these numbers. They'll instead focus on the monthly payment. So the monthly payment, I'm going to abbreviate that, would be equal to the total amount of the loan divided by the number of periods. So if it's the $12,833.59 divided by 60, your monthly payment would be $13.89. Whereas if you're choosing to do a 6-year plan, 1,490.18 divided by 72. Nope, hey, I said divided by 2 would be $187.36. So you're paying less per month, but you're paying significantly more based on the price of the vehicle over the span. And if you scale up this car price, it doesn't scale linearly. So it's not like if you have a $20,000 car, you would be paying $6,000 extra in interest. It scales exponentially. It would end up being, I think, $9,000 or $10,000 of interest, compared to if you do the 60-month plan, probably $6,000 or $7,000 of interest. So depending on how expensive what you're buying is, it changes a lot. Now, this is the easy way. We're just plugging and chugging here. I want to ask you a question that's a little more interesting. So let's change this a bit. Let's say that you deposit I don't know, $100 into a CD. Is a certificate of deposit. It's not really a savings account because you can't take your money out whenever you want, but it has a higher interest rate than a savings account. Well, say this has a 2% interest rate. That seems really high. You guys haven't paid any attention. Savings accounts in America have interest rates of 0.02 or 0.2% usually. Anyway. So this is a more interesting question. How long take double in value? This is going to require a logarithm again, like the last example we went over. So doubling in value means $200. So the amount is going to be 200. Principal is still 100. The inside of the parentheses here would be 1 plus 0.02. And again, this is going to be, let's say it's compounding quarterly to compounding monthly. If it were compounding quarterly, there'd be a 4 down here. Quarterly means 4. So 0.02 divided by 12, and this is going to be to the power of, we don't know. So I'm going to call this T because that's what we're trying to find, is how many months in this case it would take. So divide both sides by 100, and this 1 plus 0.02 divided by 12, I'm going to break that down into an actual decimal. Whenever you do that, you want to make sure that you're going at least 4 decimal places with a logarithm. The reason that you want to go 4 decimal places is, in this example, if you only go 2, it would be 1.00. So we want to go 4 decimal places. So 0.0017 to the power of t. And again, I want to use that property of logarithms. If you didn't watch the last video, in general, 2 to the third equals 8. Rewriting this in logarithmic form, base of the exponent becomes the base of the logarithm. The result is what the logarithm is being taken of, and exponent is the solution to that. So rewriting this using logarithmic form, it would be log base 1.0017 of 2 equals t. Here we can use the log base change formula. So the log base change formula says, since your calculator can only do log base 10 or log base e, we can do log of 2, and this will be equivalent to log base 2 of 8. So here I'm going to do 2, and log is log base 10, log of 1.07. Whatever I get from that is t. Let you guys watch me fumble with my calculator? Probably. So t in this case is 0.8, and we need to make sure that we know the units in this case. It's not years, it's months. 108, which is how many years? Hey. So 34 years. A little more than 34, but about 34 years. Thank you, open board. Okay, so that's reviewing interest rates and how they kind of apply to this whole thing, and also a super short review of logarithms. If you didn't catch that, maybe watch the last one on exponential decay, and that might. So we have an assignment, a paper assignment that covers this. This will be on the quiz, the Toydarian Junk Dealer, and this is part of the book assignment. So if you have any questions, feel free to let me know. And